Hi everybody, Thad Roberts here, and I've got a riddle, or nature's got a riddle, and I've got something that might count as a hint to help us solve this riddle. Now, I don't have a solution, but I'm making this video to try to give a little more publicity to this concept that somebody else came up with. I'll give it a little more attention, so maybe somebody out there has got enough creative spark in their imagination to figure out what this is actually telling us. Now, a little background. Cosmologists break up the matter-energy content of our universe into dark energy and dark matter and baryonic matter or normal matter. So all the things that are normal to us, everything that's made up of atoms, is baryonic matter, the entire periodic table of elements. Now, if I put up a list of the fundamental or elementary particles that make up all the atoms in that periodic table, it looks like this. Now, we've got fermions and bosons, and among the fermions we have two kinds, quarks and leptons. Now, in normal matter, the things that are most common for us would be the up and down quark. If you take two ups and one down, you get a proton. If you take two downs and one up, you get a neutron, and then electrons, and you can combine all these to make everything in the periodic table. All right, but we also have less long-lived particles. They're cousins to each. Like, look at the electron there. We got a muon. Muon's related to the electron. It has the same charge, but it's got a different mass. And a tau looks very much like a muon or electron also, with also a different mass. Now, all of these have very specific masses, all of these fermions, and there's a very fundamental question about why they have the masses they have. There is no theory yet that actually predicts these masses. We measure them and we put them in, but we can't explain why they have the masses they have. If we want to explain the masses, or a relationship between the masses, where would we start? Well, this guy in 1982, Yoshio Koide, and I'm probably butchering his name, so I'm just going to call him Yoko from now on. He came up with what we now call the Koide formula, or mass relation, in which he noticed that if you take these three masses, if we start with the electron and the muon and the tau, and you take the square root of each mass, so the electron mass, square root of that, square root of the muon mass, square root of the tau mass, and you treat those three square roots as fundamental values. Instead of their masses, the square roots masses. And then you combine them in this following way. You take the sum of the squares of each, and you divide it by the square of the sum. Okay, so that looks like this. Then we're going to set this equal to something. But before we do, let's pretend we have no idea what the masses of each of these are. We don't know what the values are at all. And now, what are the limits to this equation? If you go all the way one direction or the other direction, how could this thing possibly change? It could be completely hierarchical, or they could be where there's no hierarchy and they're all basically the same value, whatever that value is. Well, it turns out it doesn't matter what the values are. What matters is what's the hierarchy between them, right? If you pick all of them equal 5, you get an answer that's the same as all of them equaling 2. Try it out. So you get 1/3. That's one limit. If there's no hierarchy at all. What if there's extreme hierarchy? What if one of these things is so much larger than the rest, it's basically the other two are nothing? So you put 0 and 0 and 1. Doesn't matter which one you put the 1 on. And so you get 1 up top. And then you get 0 and 0 and 1 squared, you get 1 on bottom. So you get 3/3, or 1. So the limits of this equation are 1/3 to 3/3. Now, Yoko, my nickname for him, chose to pick the solution as smack dab in the middle as 2/3. He just set this equal to 2/3. Now, that's pretty bold. It's also really interesting. It's making a suggestion that nature has a relationship between the formation of these three particles in a way that it puts it right in the middle of the possible hierarchy arrangements. What does that mean? Why? What's going on in that formation process that would do that? What does it mean to claim that that's going on? That brings up some interesting questions. All right, well, it's important to note that when Yoko proposed this, the tau mass was only badly known. which means that he could then use this equation to predict tau mass out to several more significant digits. Let's take a look at this. This is the values, the set of values that were known at the time. Okay, and this is what he was able to predict. The mass of the tau particle was this value out to there, based off knowing the other two, based off knowing this relationship between them. Today, we've measured the value of the tau out to higher precision, and so far, within our error bars, Quixote is still right. We're at 5 to 6 significant digits now, where this relationship holds up exactly. In the words of Francois Gaffnier, the accuracy of the relation has no equivalent in any other proposed model or pattern. This is really significant as far as projecting a relationship that could give us insight of how these masses come about. This is very likely more than coincidence. There's something suggestively going on here. At least it's enough to spark my curiosity. I feel like the odds of this just being coincidence are really slim, and it kind of smells of a deep hint to me, some sort of peek into what's going on behind the curtain. And I'd love to blow that whole thing open and really understand what's going on, and so I'm trying to solicit a bunch of help from you. Do you have any insight that might help? Any suggestions here of why this relationship holds? Okay, here's things to keep in mind when you're trying to figure that out. Why is it the square root of masses in this formula? Why are they treated as something fundamental? What does it even mean for the square root of mass to be something fundamental, right? We commonly treat mass as a fundamental property, but I'm very unfamiliar with anyone treating the square root of mass as a fundamental property. Why? What is that? Maybe if we have a better insight of what mass is, the square root of mass will be an automatic thing we can tack on, say, I understand what that is, and that's why it's significant in this case, in the generation or the relationship between the generation of these 3 different particles. Also, why is the mass of each particle in this group perfectly related in a hierarchical way that's right between extremes of hierarchies? Okay, right in the middle. Why would the square root of the mass of each particle depend on the square roots of the mass of other particles? Like, what's the connection there? Here's where things get even weirder. If we apply this same equation to 3 different particles, the 3 heaviest quarks, the charm, the bottom, and the top, we also get, within current experimental uncertainties, a relation that still satisfies the equation, still equal to 2/3. Okay, but barely. Well, what about if we take the up, down, and strange quarks, the lightest quarks? That one doesn't work. Okay, maybe that means this whole thing was a coincidence. Maybe it's off, and it just, it worked out for the other 2, especially for the first one, really accurately. But then again, Francois Gaffnier, if you read his chapter 3 in his publication titled A Bottom-Up Approach to Fermion Masses, you see that he believes that Quixote's mass relation is actually only valid for the running masses, not the physical or pull masses. Okay, these things, the running masses, for example, of the charged leptons, are quite stable under renormalization, so there's not much change there, so that's why it would work. But for the heavier quarks, the transformation starts to be noticeable, and for the less and lighter quarks, it's quite significant. Okay, so the trouble is, these things are energy dependent and not easy to nail down, so we can't tell whether or not his proposal is right. But it's possible that his insight is, hey, this equation actually works for all of these groupings, but it's actually for the running masses. Okay, so that's it. That's the idea, or that's the insight for our riddle. The riddle is, why do these fundamental particles of baryonic matter have the amount of mass that they have? What sets the mass? And why does it look like there's a relationship between these masses, relationship set forth by Quixote's equation, and what does it mean? What does that relationship imply? If you have any suggestions or insights or ideas about why this relationship holds, or if you have any ideas about why this just happens to be a coincidence, why it is this way, but it's not a genuine relationship that actually holds, I look forward to your comments. Thank you. If these sorts of questions are fascinating to you and you'd like to explore more of the unsolved riddles in nature, check out my book, Einstein's Intuition, Visualizing Nature in 11 Dimensions. Or check out some of the links below to get a more brief introduction to these fascinating topics.